Up until this point, we've gone through solving linear equations and graphing linear equations and hopefully connecting those two ideas together. Now in this next unit, we're going to get into writing linear equations given a graph or given data about a particular relationship. And this is where we can really start to see where our algebra is practical in that it applies to and models the world that we live in. So we're going to start this by writing equations using slope-intercept form, and we're actually going to do a couple of lessons on this where we use this form, and this is from our, I don't know why it always does it, like the very first thing I want to write does not write on the screen. In the last lesson, we introduced this form for the equation of a line. This is called the slope-intercept form because the m is a number that represents the slope and the b is a number that represents the y-intercept, which we want to keep emphasizing is a point. It is an actual ordered pair on the line. It's where the line crosses the y-axis, and that's why the x-coordinate is always 0. And it's also what allows us to get away with thinking of the y-intercept as a number. We get a little bit sloppy about that. So the most simple version of this kind of problem that you could see is if somebody just tells you this is the slope and this is the y-intercept, write the equation. If that's the version of the problem that you get, then you would just take whatever number they told you was the slope and you would plug it in for the m, and whatever number they tell you is the y-intercept and you would plug it in for the b. So for example, write an equation of the line whose slope is -2 and whose y-intercept is 5. Years ago when I taught a physical science class, I really tried to teach my students a method for problem solving. So that was like a science class, but it was a science class where we dealt with some pretty basic formulas and such. And one of the things that I would tell them to do as their first step was list your givens. And I think that's because when I was in high school, the teacher that I had for physics really emphasize that to us. Like the first thing you do is you list your givens. So in this problem, here's one of our givens. The slope is -2. And by listing the givens, what he meant was create a list where you use the appropriate symbol and assign the values to as many variables as you have. So we have the slope is -2. So I write down m equals -2. And then we have the y-intercept is 5, and the symbol for the y-intercept is b, and that is equal to 5. And so by writing it like that, what you're doing is you're training yourself to interpret the written problem in terms of the numbers in it. Then he would make us write down the formula that we were going to use, which in this case would be y equals mx plus b. And then we actually had to do a step where we would solve for the unknown. He did not want us plugging anything in until we had solved for whatever variable in that formula we were looking for, but that doesn't apply in this case. So for this kind of problem, you would then just simply plug in your numbers. So m is -2 and b is 5. And you have written your equation for the line. That's pretty much the most basic type of problem that you could see, and oddly it's one of the kinds of problems that a lot of my students will get wrong because it is so simple that they kind of fall into that trap of thinking the problem has to be harder. It can't be that simple where I just write down the numbers. Well, yes, it can be that simple. Now the next version of this could be if you are shown the graph of a line and then asked to write the equation from the graph. So here we have an example of that. I did try to put, it's really hard to do on the device that I'm using to record this lesson, but I tried to put the scaling on here because you want to make sure you know what you're counting by. You do default to a 1 if it's not specified otherwise, but I thought it was a good idea. We'll just make sure we specify that we are counting by 1s on this particular coordinate plane. So looking at this, if the graph is drawn well, we can actually find the y-intercept from the graph. And so this is where that vocabulary becomes so important, that you know the definition of the y-intercept. The y-intercept is the point where the graph crosses the y-axis. Then if you're looking at a graph, you can identify the y-intercept just by looking at it. So in this case, we can see that the y-intercept is the point 0, -4, or you could simply write b equals -4. And we can get the slope from the graph itself. And at this point, we've done this several times. So I'm going to pick 2 points on the line, and what you're looking for are what are called lattice points. Now you can tell where my lattice points were because when I graphed this, I put some dots on there. Sometimes you don't see the dots, so I'll give you an idea what that looks like on the next slide here. But we're going to count the rise over the run. So I'm going to count up 1, 2, 3, 4. So remember your slope is rise over run. So we're counting up 4 and then over 2. 4 divided by 2 is 2. And that brings us back to this spot in the previous problem where we had the M and we had the B. Now we have the M and we have the B. And so we can write down our formula and we just plug in the numbers into the appropriate spot. You can write y equals 2x minus 4, or if you would like to, you can write plus -4, and that retains the plus sign and it retains the negative on the B. Either one of those would be equally correct. Now, there are obvious disadvantages to doing this from the graph. The first being that some numbers are terrible. And so if you saw a line that looked like this, okay, you can't get the y-intercept because you can't see where it is. It's somewhere between 2 and 3. It's closer to the 2 than it is to the 3, but whether that is a quarter of the way, 0.2, 0.3, there's no way to know from the graph, okay? Now, if you did want to write the equation for this line, you would need to use what I call like the nice friendly points called lattice points, okay? And this is actually for a future lesson, but if you look right here where I'm pointing, you can tell that that line clearly goes through this point, all right? That's what we call a lattice point. It's a point where we can come up with knowable coordinates for that point. And then what we would do is we'd scan the line looking for another lattice point, and that looks like a pretty good candidate right there. And I just did this on a lark, okay? And you could kind of work from there. So you know at this point that you could find the slope of the line given those 2 points because we've worked with that. So when I said looking for those lattice points, looking for the lattice points on the line, that's what you're looking for, okay? Even if there's no dot there, okay? When I originally drew that line there were no dots there, but that doesn't mean that the point isn't there. So that's pretty much the content for this particular lesson, is just being able to pull the M and the B from a graph or from given information, and then write the equation from there. Since this is a really short lesson, I thought what we could do in this lesson is actually make some application. So I haven't really steered these videos towards the application. You'll notice we haven't really done word problems or anything. I've tried to focus on the mechanical aspect of being able to carry out these operations and these procedures efficiently. And then in your actual algebra class, that's when your teacher might give you the application problems and you would have the mechanical skills in place to be able to do it. This is actually a pretty good opportunity to look at some of the things that are modeled with linear equations and how we can write equations back on, about those. So I'm going to photograph 2 problems and hopefully upload them to the next few slides so that we can go through them and talk about them. Okay, so this first example is renting a compact car, and this is one of 2 really common scenarios that you will see like linear equations for. So it says the Star Car Rental Company charges a flat fee of $30 plus 25 cents per mile to rent a compact car. Write a linear model that gives the total cost in terms of the number of miles driven. Okay, so let's start with listing our givens, like kind of getting our head around what this problem is saying. So it says here that there is a flat fee. And so I'm going to write over here flat fee equals $30. Okay, you could just write flat fee equals 30 if you want, since we understand in this problem that we're dealing with money. And then we have plus, okay, so I'm going to circle that. That means that probably we're going to have a plus sign in our formula somewhere. And then we have 25 cents per mile. So I guess I'll write that plus, I hate that I do that, 0.25 per mile. Okay, and what I did there was I changed the 25 cents over into dollars so that I would be matching up and I wouldn't be doing like dollars in one part of my problem and cents in the other part. So one thing that you want to do when you're approaching a word problem is recognize if you're getting tripped up on it, where you might be getting tripped up on it. So if you don't know what a flat fee is, that's going to hamstring you to solve this problem at the get-go. And it's a question that you would want to ask your teacher and just say, Mr. or Miss So-and-so, I don't know what it means when it says a flat fee. What is that? And it gives you an opportunity to ask a very specific question that's going to help you understand what you're reading there. So a flat fee means that if you're going to rent a car from this company, you are going to pay $30 up front, even if you never drive this car anywhere. Okay, I don't know why you're renting a car if you're not going to drive it, but even if you don't drive the car at all. Okay, and maybe that covers like maintenance fees, it covers the desk clerk, they're trying to make a profit here. Now, when you start driving that car, you're actually putting some wear and tear on the car, and so they're going to charge you for that, the distance that you drive. Okay, so if you're only going to drive that car for 10 miles, you're going to use it to get home and to work for a day while your car's in the shop. It's not going to put a lot of mileage on it. If you're going to actually rent this car and take it on a road trip, it's going to put more wear and tear on the car, and the company is going to want to charge you for that. Okay, so write a linear model. This is a fancy way of just saying write an equation, and if you weren't sure, you could ask your teacher, what does it mean by a linear model? Or you could just take a guess, okay, and say, well, I've been studying equations. I'm going to guess that my model is an equation. And it's asking you to relate the total cost in terms of the miles driven. So here's what I'm going to do. I'm going to start with the total cost. I'm going to use T for total cost, because even though we use X and Y most of the time in our math classes, we often substitute other variables out when we're doing application problems to represent whatever it is we're actually measuring. So the total cost to rent this car is going to be that flat fee of $30. And you can actually walk through the timeline with this. You go to the counter, you fill out the paperwork to rent your car, and you hand over $30. Plus, now it's going to be 25 cents for every mile that you drive. So if you only drive 1 mile, you would pay 25 cents. If you were going to drive 2 miles, you would pay an additional 50 cents. 3 miles, you'd pay 75 cents. 4 miles, and you'll pay an extra $1. Now, looking at the pattern there, what you're doing is you're taking the 0.25 and multiplying it by the number of miles that you've driven. So you could more efficiently just write that as 0.25 m. Just kind of follow through with the reasoning here. If you don't drive any miles, then it would just be 0.25 times 0, which would just leave you with the $30. 1 mile, you would be adding 25 cents. Multiply by 2 for 2 miles, you'd be adding the 50 cents, and so on. Now, some people, technically your problem is done, they'll switch the order of that. And the only reason they're switching the order of that's using commutativity of addition, is to make it look like that y equals mx plus b form, okay? And so you'll see some people that will use the x and the y instead. And really all of that is just a matter of personal preference, like which way you want to write it, which variables you want to use, unless you're specifically instructed to do it a certain way. There is nothing more correct about this than this. Okay, what's important is that you understand how this equation models the situation there. Now, I know you guys can't see the problem numbers there, but it says use the equation to fill in the table. So we go from the verbal description to the equation to the table, and then of course from the table we could go into a graph. That if we were doing 25 miles, we would plug in 25 for the M, and then multiply it and then by 0.25 and then add the 30, and you could complete the table, and then you could also graph the relationship as well. It's a pretty simple relationship to graph, so you might be wondering, well, why would you want to graph that? Just probably in this situation you wouldn't, but there are linear relationships that you would want to. Let's take a look at another one. All right, I really like this one because I think this one gives us the opportunity to think about a problem and think of the different ways that we can represent the problem to figure it out. So it says at noon, you are 200 miles from home. You are traveling home at 50 miles per hour. Write an equation that gives your distance from home, y, in terms of the time, t. Let t equal 0 correspond to noon. Why does the line given by this equation have a negative slope? So actually pause the video for a moment and think about this problem for a few minutes. See what you can do to try to come up with it on your own, and then unpause the video and we'll take a look at this together. All right, and I actually redid this and I moved the problem down here because I wanted to use my coordinate plane higher up. So, all right. So if you have trouble processing this, one of the things I'll tell my students all the time is try drawing a picture. Try graphing it. See if you can find a way to represent the information in this problem in a way that's going to make sense to you. So what I'm going to do is try to graph it. And honestly, I haven't worked this problem out in advance, so this is like a bold and risky move for me, recording the video. So what I'm going to do, it does tell us that the distance from home should be the y-axis. So my distance from home, I'm going to look at how much space I have to work with here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, about 10 tick marks. What I'm going to do is make each of these tick marks worth 25 miles. Okay? So 25, 50, 75, 100. 125, 150, 175, 200, and that would be 225. And then it tells us in the problem that we are traveling 50 miles per hour. And so I'm going to scale this way. So that was terrible. Let me see if I can do a little bit better than that. There we go. It's a little bit better. I'm going to make each one of those worth 1 hour. Okay. And what I'm doing here is I'm working with the coordinate plane that I have. Remember that you do have to specify your scale. You default to ones unless it's indicated otherwise, and I'm definitely using it otherwise here because my coordinate plane doesn't go up to 200, nor do I want it to. And so what I'm going to do here is try to graph this relationship to see if it helps me see what the equation might be. Now, it tells us in the problem that at noon, we are 200 miles from home. And then it says, let t equal 0 correspond to noon. And so right here, when the time is equal to 0, that's noon. Okay, so I guess I'll put that on here. That's noon. And it says that at noon, we are 200 miles away from home. And so what that did right there was it gave me my Y-intercept. Okay. Now, it also says that we are traveling home at 50 miles per hour. So after 1 hour goes by, I'm going to have traveled 50 miles, which means I will only be 150 miles from home. And so that would put us right there. After 2 hours, we'll travel another 50 miles, so we'll only be, what would be awesome is if I put that dot in the right spot. There we go. Not my best work. After 3 hours, we'll have gone another 50 miles, and after 4 hours, we should be there. And I'm just gonna go ahead and put that other dot down there, and you're probably thinking like, Miss Taylor, not sure about that. Okay. So now that I've done this, and really I haven't done anything in terms of like writing an equation, all I've done here is try to take this information and put it on a graph so I could see it differently. Now that I've done that, I can see that my y-intercept is 0, or 0 is 200. I don't know. And I have enough information to be able to get my slope. In fact, I can actually get it from the graph. You just want to make sure that you attend to the scaling. My rise is -50, not -2, because you got to remember what you're counting by. And my run is 1. Again, not 2, because you got to remember what you're counting by. And so my slope is -50, which means that my equation is y equals -50x plus 200, or you could say distance from home is equal to -50 times your time plus the 200. Okay, and again, this is a matter of personal preference. You could also use the slope formula there to figure it out. I thought this was just a really good example of a way that you can use the graph to help you visualize what's happening. Now, there's a question there. We want to make sure we answer all the questions. It says, why does the line given by this equation have a negative slope? So what is the meaning of the negative slope? Well, it's distance from home, and we are traveling towards home. And so you might answer that because we are like decreasing the distance to home You could say because of the direction you're heading, and that is really tapping into some physics ideas where the idea that the direction matters. And if your line were to do this, it would mean you would be heading away from home again. Now, I did put the arrows on here, and this is actually an example of a time when you might not want to put the arrows here because certain things don't necessarily have context. And so you can't have negative distance to home. Now, some people might say, well, does this mean that you're heading away from home, but now you're in the other direction? So maybe you're east and you're heading west to home, and now you've passed home and you've gone west. Absolutely, there are ways that you can think of it that way. Not really specified in this problem. So this might be one of those times where you might actually want to just truncate your line and like not put the arrows on there because of the context of the problem and what it represents. All right, so that wraps up this lesson. I'll put a few problems on the screen for you to practice with, and then you can pause the video, practice, and check your answers when you're done. Forgot to put the problem number there. All right, so we have just 7 problems. Write the equations of the following lines. So for the first 3, you're given the slope and you're given the y-intercept. So slope of 3, y-intercept of -2, slope of -1/4, y-intercept of 1, and a slope of -1, y-intercept of 3. For the next 3 problems, you're given the graph, and just keep in mind, I put the dots there so that you could see where the points are. I'm aware that it might look a little bit sloppy there. And then number 7 is another word problem. The Maple Car Rental Company charges a flat fee of $45 plus 35 cents per mile to rent a full-size car. Write a linear model that gives the total cost in terms of the number of miles driven. So that is similar to the example problem that we did earlier. Pause the video. Shouldn't take you too long to do these. And then check your answers when you are finished. Right, so for the first 3, y equals 3x minus 2, or 3x plus -2. y equals negative 1/4 x plus 1, and y equals negative 1x plus 3. You don't need the 1 there, though, because negative 1 times x would give you negative x, or the opposite of whatever x is. So you could just write negative x plus 3. Not a bad idea just to remember that if you do see the negative x, that it could be written as negative 1x. For the next ones, y-intercept is 3, and we count up 3 over 1, so y equals 3x plus 3. For this one, we count down 2 and right 3, so the slope is negative 2/3, y-intercept of 2, y equals negative 2/3 x plus 2. And for this last one, the y-intercept is negative 1, and I count up 2 and over 2 to get to my new point, which is 2 over 2, which is 1. So you could write y equals 1x minus 1, or just y equals x minus 1 would be fine as well. And then the last one, we have the total cost is equal to the $45 flat fee plus 35 cents times however many miles you are driving. You could also elect to switch the order of that since addition is commutative, and you could replace, I meant to replace this with the next one, I wrote it. You could also replace the t and the m with an x and a y if you're more comfortable with that. So y equals 0.35x plus 45. All right, so that wraps up our first lesson on writing equations of lines.